This is another proof type we're going to be looking at here. And we're also going to be kind of reviewing recursion. You guys have taken 1410, so you know what recursion is. My question for you is, how good is your recursion? Yeah, that's typically the answer. Thumbs down, yeah. Recursion takes practice. That's all there is to it, and we're going to get some practice in today. But it takes practice to wrap your head around it, and hopefully we'll see some stuff that'll clear it up. We're going to take a look at what is a proof by mathematical induction. We're going to look at recursive functions, as in f of x style functions, mathematical functions, and then recursive algorithms, which are basically functions too, but computer programming functions. And then we're going to do a proof using mathematical induction to prove the truth of an actual algorithm. That's the last thing we'll do. Hopefully we'll get to all of that today. So here's a basic idea. I want to show you this quick, fun little video, and then we'll talk about what this is all about. This is like a 30-second video. So, dominoes. Do you ever play with those when you were kids, stack them up? There was a thing when I was a kid called Domino Rally. Does anybody know what that is? They're dominoes that were connected to a track. So you just connected the tracks. The dominoes, you could just tilt the track and they would all stand up. And so you didn't have to set them up manually, right? So you just put together a whole bunch of tracks and you have this really cool, I'll see if I can find them later and show you a picture of them. But anyway, why do we bring up dominoes? Because the idea of mathematical induction is this. As you see with the dominoes, if they're lined up the exact same space apart and one domino can reach the next, then that one can definitely reach the next, right? So you guys agree with that premise? So if I can reach the first one, I can reach the second one. If the first one will knock over the second one will knock over the third one, assuming they're all spaced exactly the same distance apart, right? The other metaphor you might hear is a ladder, where if you have an infinite ladder, right? That's a pretty big ladder. And if I can reach the first rung of the ladder, and they're all evenly spaced, all the rungs are evenly spaced. If I can reach the first rung of the ladder, and from the first rung I can reach the second rung, and from the second rung I can reach the third rung, then by mathematical induction I can reach every rung on the ladder. It would take an infinite amount of time, but I could do it, right? You could use the same metaphor with stairs, right? If I can reach the first step, and from any given step I can reach the next step, then you can, by mathematical induction, you can reach every step. That's the basic premise of what mathematical induction is. We're going to look at plenty of examples here in just a minute. So, and this is we're actually going to do sort of just a verbal proof here. Prove that it's possible to reach every step of an infinite staircase given the following. That one, we can reach the first step. And two, if we can reach a given step, we can reach the next step. That's the premise I just set up a moment ago. So how would we do this proof? Well, there's two steps in a mathematical induction proof, now three. Per rule number one, we'll talk about the steps in a minute. Per rule number one, we can reach the first step, agreed? That's what the rule, those are the givens, right? Per rule number two, we can reach the second step, agreed? Yep. Okay, per rule number two, then we can reach the third step, right? And then per rule number two, we can reach step n for all positive integers n, right? That's a pretty simple way of putting it, and that's just a more formalized way of saying what I said a minute ago. But do we all agree with that basic premise? Okay, now we have to do some actual proofs here to prove that this technique works when you're trying to do an actual proof. But we're all on board with this? We good? All right. So the idea is that you can use mathematical induction to prove that P of n is true, whatever P of n is representing, for all positive integers n, where P of n is a propositional function, right? Back to our early days of propositions and predicates and all this stuff. This is how the purpose of mathematical induction. So questions about the basic premise? We good? All right, so mathematical induction steps. to prove that P of n is true for all positive integers n, here is what we do. First, we have the base step. Does that term sound familiar? What's that remind you of?
Base case and recursive.
A base case and recursive function, exactly right. You're going to see some very eerie similarities, right? They're very similar, okay? So first of all, we're going to prove that P of 1 is true. Well, typically, what's P of n going to look like? It's going to be some formula, right? Well, we'll just plug in 1 and see if the formula holds true. That's easy to prove, right? It's just an exhaustive proof of one thing, right? I don't know if that's the best way to put it, but that's the idea. The second thing then is the inductive step. Now this is tricky stuff here. Look at our formula there. What is a proof all about? Remember, all proofs, all in quotes, most proofs have this form of something, therefore something else, right? Our P, therefore Q. And the only thing we care about in a proof is if P occurred, then Q should occur, right? So take a look at what we have here. We're going to prove that if P of K for some arbitrary K is true, therefore P of K plus 1 will be true. Does that make sense? Okay. Now, we're not going to prove that P of K is true. We're never going to prove that. Okay. What we're proving is that if it's true, that P of K plus 1 will also be true. That's a very important distinction. All right? Make sense? And this goes back, somebody in this class earlier was asking about, I think it was Kyle, he's not here, but he's sitting over here. He was asking about universal generalization, where we get to this situation where if it's true for some arbitrary value, we can generalize it for everything. And we've seen other examples since then about this, but this basic idea is a very good exercise in that, where we're taking and proving it true for some instance, and then we can generalize because of that, right? Some arbitrary instance. All right. So with the inductive step, the first thing that we're going to do is assume that P of K is true for some arbitrary K. We're just going to assume it. What is the value of K? Doesn't matter. Just some arbitrary number that's in our domain. All right? We're going to assume that that's true. Then, assuming that the above is true, we're going to prove that it will be true for P of K plus 1. And then we're just going to do this with a mathematical proof, just a regular old proof like we've done before. Whatever proof we need to use. Most of these are just going to work out with a direct proof, right? So that's the idea here. Now, assuming that P of K is true, right? When we make that assumption, there's a term for that. We call that our inductive hypothesis. That's an important word to understand. The assumption that P of K is true is what's known as the inductive hypothesis. Remember, in a P, therefore Q, what do we call the P in those? I'll give you a hint. It's half of that green text up there. The hypothesis, right? In a P, therefore Q statement, the P is the hypothesis and the Q is the conclusion, right? In this case, because we're using a particular type of proof, it's called the inductive hypothesis, right? All right, so once steps 1 and 2 are done, then we've proven that for all n, P of n is true for the domain of all positive integers, right? That's using universal generalization. Good? So before we get into an actual proof, I want to make sure this premise, we're buying into this, that you're not just believing me, that it makes some sense. We feeling okay about that? Yeah? Any questions about this? So now, what we've done here is we've proven that for all k, if P of k is true, then P of k plus 1 is true. That's what we will do with our proof. When we've proven that, then we've proven this. So take a look at what we have here. We have this whole thing, therefore this whole thing, right? So this is a P, therefore Q, but within our P, we have another P, therefore Q, right? So what we're saying is that if P of 1 is true and P of K, therefore P of K plus 1 is true, therefore this is true, right? So that is how we generalize, that's how we got to this earlier, just a moment ago. Does that make sense? I'm getting a couple blank stares. We doing okay with this? Good? All right. I just want to make sure if there's anything fuzzy here, when we move into actually doing a proof, your heads are going to explode. Sorry. You're These are tricky proofs. They take a while to kind of wrap your head around them. All right, so an important note to make sure we understand. We do not assume that P of k is true for all positive integers. That's what I mentioned a minute ago. We're not assuming that it's true for every single number, right? We're just picking some arbitrary k. What is k's value? I don't know. Who knows? It doesn't matter. It's just an arbitrary k, right? All right, so that's important. And then the second thing is, we only show that if P of k happens to be true, then P of k plus 1 is true. Remember, that's how a proof works. We don't care about Q if P never happened, right? That's how proofs, the whole point of a proof, and I know I say this every time we talk about proofs, right? But the whole point of a proof is that I want to know if this thing occurs, will this other thing occur? In fact, I want to prove that if this thing occurs, this other thing will occur. So let's assume that this occurred. Well, because it occurred, did these other things happen? That's it. That's what a proof's all about. Okay, questions about this premise here. We're laying some pipe here, setting the stage, making sure we understand it. We good? All right, so let's take a look at an example here. Mathematical induction, example number 1. We're going to prove that n cubed minus n is divisible by 3 for all n, where the domain is positive integers, okay? So n can be any positive integer. So in other words, 9 cubed minus 9 is divisible by 3, and 4,332 cubed divided by, or minus 4,332 is divisible by 3. That's what we're going to prove. Every single number for infinity. That's one of the beauties of a mathematical induction proof. You can prove it for everything, okay? So let's first of all state this in a mathematical sense that makes some sense, in a mathematical way that makes some sense to us. So how could I restate our proof statement up there, what we're trying to claim mathematically? So I want a formula that states that n cubed minus n is divisible by 3. So what does that look like? How can we describe something that's divisible by 3 in mathematical terms? Okay, yeah, we can show 3 as a factor, good. So here's how we might do that. We could say that let P of n be the statement that n cubed minus n is equal to 3m, right? Where m is just some number in the set of all integers. Notice that's not just positive integers anymore, all integers. Would you agree that that statement means that it's divisible by 3? We don't know if it's true yet, but would you agree that that's what I'm claiming, right? We agree with that? Okay. So now, what's our first step? The base step is to prove that P of 1 is true. Well, that's easy, right? We just plug in 1 and see if it's true. And there's not a whole lot of work there, right? 1 cubed minus 1 is equal to 0. So is 0 divisible by 3? In other words, can 0 be represented as 3 times some integer m? Yeah, what is that integer m? 0, right? It just happens to be the same number. That's a coincidence, but yeah, works out just fine. So can it be written that way? And yes, it can be. 3 times 0 that's our 3m, okay? So m is 0 in the statement 3m. So there, we've proven our base case to be true. Easy. Now, what's step 2? I'll give you a hint. It starts with n and ends with induction. Induction, good, man. How'd you guess that? That was good. All right. So yeah, the inductive step, right? So the second step, we're going to prove, this is the inductive step, that if P of k is true, then P of k plus 1 is true for some arbitrary integer k. That's the inductive step, right? We assume P of k to be true, and then we're going to prove that if it's true, P of k plus 1 is true. So how the heck do we do this, right? This is just a direct proof now. So forget about this whole inductive business and all that. How do we do a direct proof? What do we do? Think about some of the direct proofs we've done in the past. We take the variables that we know and we just start plugging and playing and start doing some algebra, right? Does that ring some bells? Yeah? So let's start doing a little bit of plugging and playing here. Let's see what we can do. Our inductive hypothesis is this. We're saying that P of k is true. We're assuming that it's true, right? That's our inductive hypothesis. Would you agree that if P of k is true, that that is true? K could be anything. Remember, we're assuming that K is true, that P of K is true. We don't know if it's true. But if it were true, would you agree that that statement is true? But remember, look at our formula here. I'm glad that you're asking this because this is where it gets tricky. So this is what we're claiming here, right? This is our premise. So how did we prove it for 1? Well, I plugged in a 1 here, which means it puts the 1 here and the 1 here, right? So in this case, I'm plugging in a K, which puts the K right here, and that means that we have K cubed minus K, right? We don't know if that's going to evaluate to be correct or not, but that's just substituting, right? So anytime, that's how all functions work. Whenever you're using a function, whatever number n is, you plug in the n and then you populate it everywhere there's an n. So if I plugged in the number 300, then that would mean I'd be saying 300 cubed minus n, or minus 300, right? So in this case, I'm not plugging in 300, I'm plugging in k. So I'm saying k cubed minus k, right? So remember, all proofs, P therefore Q, right? P therefore Q. We don't know if P is ever true. We have no idea. All we're saying that is if it is true, is Q also true? That's how all proofs work, right? If P is true, then also Q is true. So when we write a proof, we assume that P is true. We just assume it's true. Because if it isn't, we don't care. We don't care what happens with Q if P is not true. So in this case, remember our original our point that we were looking at a second ago was that we're trying to prove that if P of K is true, therefore P of K plus 1 will be true, right? Okay. So P of K, let me see if I can this would be really nice if I had my little stylus I can write on the screen here. Let me pull up a little, get out of this mode here. Pull this up here. So remember, the whole point of this type of proof, I'm going to make that's our arrow there. I guess I could just go back a few slides, but okay. This is where the whole way mathematical induction works is if that's true, then this will be true. We don't know I have no idea if that's true. We never will. Okay, that's not what we're trying to prove. We're proving in the event that that's true, this will be true.
So what if we take a premise like is K even?
Well, I don't want to jump into the middle of another proof while we're in the middle of this proof, right?
So we're just paying attention for this specific case where you have the premise n squared minus n is
N cubed minus n.
N cubed.
Yeah, my whole thing, I've been told as an assignment or as whatever, that I am to prove that n cubed minus n is divisible by 3 for every number from 1 to infinity, okay, right? And so I've already proven it's true for 1, right? We manually just plugged in a 1, right, and that it mathematically worked out, right? I plugged in a 1, that became 1 cubed minus 1 is equal to 3 times something, right? We proved that a minute ago. So now the next step is to prove that if this is true, then this will be true.
So you would plug in 2, right?
I'm not plugging in 2. I'm plugging in K. Some arbitrary integer that we don't know what value it is.
Okay. To continue, I'm lost, but it will make sense.
Well, tell me specifically what you're lost on, because this part hangs up more people than you'd think. So
I mean, would you theoretically have to test like every?
No, that's what this proof is going to do for us. Doing this proof will prove that it is true for every single number. Or that it isn't, one way or the other. We're going to prove one way or the other.
Okay, yeah. So I guess I'm curious, how do you prove that?
That's what we're working on. So now, again, would you agree, I just want to make sure that we're agreeing with this basic premise here. Would you agree that just think of your old f of x style function with a graph in algebra, right? whatever x is, instead of n's here, just imagine an x there. Whatever number you put in here, you plug it into these variables right here, right? Agreed? Craig, agreed? Yeah. So what number am I plugging in here? Well, I plugged in 1 a minute ago. Now what number am I plugging in? K. It's just some number k, right? So if I plug in k there, then that means I'm claiming that k cubed minus k is equal to 3m, right?
Are we assuming that or claiming that?
Well, take any function in algebra. F of x equals x cubed minus x. You plug in whatever number to x, what is the whole point of plugging in x to the f of x? To substitute the x cubed minus x with whatever number you plugged in into those spots. So that's all I'm doing here. Just so happens that the number I'm plugging in is the number k, right? I don't know what k's value is, but it's just some number k, some arbitrary integer, okay? All right, so I'm just simply plugging it into the formula. That's all I'm doing. I don't know, because I don't know the value of k, I have no idea if that's going to hold true. I don't know, okay? In a function on a graph, you're not trying to prove that it's true or not. You're just plugging and playing. In this case, we're substituting n with some arbitrary integer that we don't know its value, so we don't know if this is true or not. But remember, our goal is, that's our p. That's the left side of our p, therefore q. Our goal is if p is q, then q will be true, all right? So we're going to assume this is true. In the event that this is true, let's see what happens to the q. Well, what's the q? P of k plus 1, right? All right. So we're going to calculate p of k plus 1 with the assumption that k cubed minus k equals 3m is true. Because if it's not true, I don't care about p of k plus 1. I don't care. All right. So would you agree that this is the equivalent? All I did, again, I'm just plugging in k plus 1, whatever number that is, I'm plugging it in right there. Right? I plugged in k plus 1 there, which means k plus 1 needs to go here and here. Agreed? So that means we got k plus 1 cubed minus k plus 1. All right, next up. Let's do a little bit of algebra there, and that effect was meant to show you that that is being changed to that. Like we just did all the factoring. I'm going to assume you know how to factor that, or to FOIL with 3 things, right? But all that is just the k plus 1 cubed. I did not bring in the other k plus minus k plus 1 on the left, or on the right there. So now we're adding that. Would you agree? I mean, you might want to do the math to check me, but that math is correct, right? That's just basic algebra, okay? All right, so now we have this. Now remember, what is our purpose here? What exactly are we trying to prove? Yeah. We're trying to get our formula to look a certain way, right? We're trying to rearrange this to look a certain way, right? What are we trying to accomplish, which is just what you said. We're trying to get that to somehow look something like that. Do you guys agree with that premise? Remember, all the proofs we've done in the past with direct proofs, what have we been doing? We're just trying to manipulate. We know that we're making some assumption that this is equivalent to this, and we work our way through and we manipulate things, apply rules of inference and logical equivalences, and manipulate things and you know, factor things in and out and try to make it look the way we want it to look. And it either will or it won't, right? That's just how all direct proofs work. Well, this is still a direct proof. This step is a direct proof, right? All right, so with that in mind, let's just do a little manipulation to our formula there, okay? Would you agree that that is the same as that? All I did was factor in a negative 1 into my k plus 1 there, right? See that? Do you agree with that? That's just basic algebra. But now what do we have the ability to do? I can get rid of the positive 1 and the negative 1, right? And we just get those out of there. They cancel each other out. Okay, so now we end up with this looking formula. Now, what's cool about this, look at it very closely. What can you see that we can do here? Do you see sort of the pieces of this kind of coming together a little bit? So right now we have a k cubed in our formula. We also have a minus k in our formula. Well, we can rearrange the order of this. Maybe like that. Does that look a little bit better? So we have part of our formula already. We have k cubed minus k plus 3k squared plus 3k. All right. Well, let's take this a step further. So now that we have this rearranged here, look at what is going on right here. This is this. Well, aren't we assuming that this equals this? Right? That's our assumption. We don't know if it's true, but that's our premise. We're saying in the event that it is true, when that is true. Well, if it's true, which is what our claim is, remember, this is a P, therefore Q, if P, then Q, then when that is true, then that can be substituted right here. So we can replace that k cubed minus k with a 3m. Would you agree with that? All right. Now, take the rest of this. What can we do now? Factor out a 3, yep. So factor out that 3, like that little effect there. Okay, so we factored out a 3, and what are we left with?
3 times some number.
3 times some positive integer, or some integer, right? Which is the form of an odd number, or of a number that's divisible by 3. So we've proven that when P of k is true, that P of k plus 1 will also be true. Do you agree that we've proven that? Right, so let's just clean this up a little bit. We can compress all of that stuff into some integer g, right? Just make it some integer g. And now we have the form of a number that's divisible by 3. So, since P of 1 is true, we know this to be true. That we know because we tested it, right? And if P of k is true, then P of k plus 1 is also true. Thus, by mathematical induction, P of n is true for all positive integers n. Okay? Do we agree that that works? So another way to think about this is, remember, we don't know if P of k is actually true for all integers. All we know is that we're assuming it's true for this one k. When it's true, then that square purple box has to be true. And if that's true, then that we can substitute those algebraically, the 3m for the k3 minus k cubed minus k. We can substitute that. And when we do that, we mathematically have proven that in the event that P of k is true, P of k plus 1 will also be true. We've proven that. Well, now think about it. It's true for some arbitrary k. Well, could k's value have been 1? Sure, it could have. So if it's true for P of 1, therefore it's true for P of 2. And if it's true for P of 2, therefore it's true for P of 3. And if it's true for P of 3, therefore it's true for P of 4. Right? That makes sense? Remember, step 1, prove that P of 1 is true.
Yeah.
Step 2 is we assume, step 2 is to prove this to be true.
Okay.
And remember, this is simply another, it's just one of these, right?
Yeah.
That's all it is, okay? So when we do this, and remember what our truth table looks like for this.
Yeah.
The only time we even care about this number is when that one's true. If this is not true, I don't care about Q.
Yeah.
So with this being our Q and this being our P, I don't care about this unless this is true.
Okay.
So I'm going to only look at the cases where P of k is true. So if it's ever true, if ever, maybe it'll never be true, but if it is, what we know in this case with this proof we're doing, if P of k is true, then we know that k cubed minus k is 3m. We know that, if P of k is true. If P of k is not true, then this is not true.
Okay.
But since we're assuming that's true, then this is true in the event that that's true. So if this is true, now I can mathematically, try to test this out by plugging in a k plus 1. That's where we got this foiled out or whatever, right? That's where we got this by plugging in a k plus 1 right here and a k plus 1 right here. And then we just mathematically were able to reduce it down to literally a 3m, or a 3g in this case. And so because it did come down to an actual divisible by 3 number, then in the event that this was true, which is what we assumed it was true, then this was also true. which proves that anytime that's true, this will also be true. Right? That's the whole premise of the mathematical induction. Feel good about that? Other questions? All right, let's meet Carl Friedrich Gauss. Does anybody know this name? You probably know by the last name, right? Gauss. What do we know? But what's the one thing that probably everybody knows about Gauss?
Gauss's law.
Gauss's law? Okay.
Remember we did something with Calc 2, I don't remember what it was.
Yeah, he's done a lot of things. There's one that I thought a lot of people maybe would recognize. You'll probably recognize it when you see it. But let me tell you a little bit about this guy. He was a troublemaker. When he was a kid, he's one of these guys like Einstein, right? That he can't. He didn't do well in school because it was too easy for him. It was too boring for him. So he was kind of a troublemaker, and his teacher, as a punishment, told him to, or not as a punishment, but to keep him busy. I want you to calculate the sum of the numbers 1 through 100. 1 plus 2 plus 3 plus 4 plus 5, all the way up to 100. So she told him to do that. Sum the numbers from 1 to 100. Within just a couple minutes, this kid, like in grade school, comes up with this formula right here. I don't know what the technical name is. It's Gauss's formula, Gauss's sum formula. I don't know what the technical name is for it. But he comes up with this idea that the sum of 1 plus 2 plus whatever all the way up to plus n is equal to n times n plus 1 divided by 2. Now, this is what's happening here. I don't have a visual for this next piece. But what he figured out is that take the numbers 1 through 100. Look at the first number and the last number, 1 and 100. What does that add up to? 101. Take the next numbers, 2 and 99. What do those add up to? 101. Take 3 and 98. What does that add up to? 101. And every number, 4 and 97 and 5 and 96. If you work your way towards the center, you're going to end up with a whole bunch of pairs of the number 101, right? Which is where this formula is derived from. If you take the time, so if you have the numbers 1 through 100, you'll have 50 pairs of 101, right? That's where the divide by 2 comes in. Anyway, so he figured this out, though, and he figured out how to calculate it, and just within minutes, he came up with the answer to this problem, okay? What we're going to do is prove that this is true for all numbers, that it will work from 1 through 5, 1 through 6, 1 through 90, 1 through 8 billion. We're going to prove it's true for every number, from 1 through everything, okay? Using mathematical induction. So we're going to call this function the S of n, like sum of n. Let's sum of n be the statement that the sum of 1 to n is equal to n times n plus 1 divided by 2. We want to prove that it's true for, how do we read that? We're starting with n equaling 1, and we're going to increment it up through infinity, so forever, and we're just summing up n along the way. 1 plus 2 plus 3 plus 4 all the way up to infinity. We're going to prove that's true for everything.
See you next week. Same bat time, same bat station.